Learn about total differential of a function. Suppose z is a function which varies with respect to x and y and it is differentiable at x naught y naught. Then increment of function f is notated by delta f, which is f of x naught plus delta x comma y naught plus delta y minus f of x naught y naught. Delta f, which is the increment of f, denotes change in value of f of xy when xy varies from initial position x0 y0 to a new position x0 plus delta x comma y0 plus delta y. We will make use of Taylor's theorem for function on two variables to find out the expression for f of x0 plus delta x comma y0 plus delta y. By Taylor's theorem, we have f of x0 plus delta x comma y0 plus delta y equals f of x0 y0 plus delta x into f dash of x0 plus delta y into f dash of y0 plus delta x square by 2 factorial into f double dash x0 plus delta y whole square by 2 factorial into f double dash of y0 plus etc. Where delta x and delta y are small changes or small increments for x and y values respectively. Since delta x and delta y are itself small values, we can neglect squares and higher powers of these small values, and thus neglecting the negligible values, we obtain RHS as f of x0 y0 plus delta x dou f by dou x plus delta y dou f by dou y, where dou f by dou x is evaluated at point x equals x0 and dou f by dou y will be evaluated at value y equals y0. In RHS of equation 2, we can give x equals x0 and y equals y0 wherever x and y appears. Taylor series for function on two variables can also be written as f of x0 plus delta x comma y0 plus delta y equals f of x0 y0 plus delta x fx plus delta y fy at x0 y0 plus 1 by 2 factorial delta x square dou square f by dou x square plus delta y square dou square f by dou y square plus 2 times delta x delta y multiplied to dou square f by dou x dou y at point x0 y0 plus etc. Since we have delta x and delta y are very small values, when you neglect squares and other higher powers of delta x and delta y, our RHS becomes f of x0 y0 plus delta x fx plus delta y fy at x0 y0, which is exactly same as RHS of equation 2. Thus, we obtained formula for delta f, which is the increment of function f, given by delta f equals dou f by dou x multiplied to delta x plus dou f by dou y multiplied to delta y, when f is a function on just two variables x and y. We could arrive at this equation because from equation 2, we can bring f of x0 from RHS to LHS, and our LHS become f of x0 plus delta x comma y0 plus delta y minus f of x0, which is the equivalent expression for delta f or increment of f, and thus we have delta f equals delta x fx plus delta y fy, and this is considered as the approximate expression because we have obtained this expression by neglecting considerably smaller values. df denotes total change in f or total derivative of f, or it is the total differential of f. We have total change in f is approximately equal to increment of f when function's value change from original position or initial position x0 y0 to a new position x0 plus delta x comma y0 plus delta y. Thus we have differential of f or total differential of f df equals fx into delta x plus fy into delta y, or differential of f at particular point x0 y0 is given by df equals fx at x0 y0 into delta x plus fy at x0 y0 into delta y. A quick note, RHS of equation 2 is also known as local linear approximation of function f at point x0 y0 because we are approximating function's value at x0 plus delta x comma y0 plus delta y approximately depending on Taylor's theorem, also because dou f by dou x and dou f by dou y can be viewed as tangents, and thus tangent lines are providing us approximation, and this RHS is locally evaluated at the particular point x0 y0, hence giving the name local linear approximation for function f at x0 y0.